Tonight's topic does not necessarily fit in the optics unit. However, it is on the AP exam, and this seems like the most logical place to talk about it, because yesterday we talked about the behavior of electrons in the Bohr model of the atom, and today we're going to talk about what we know about the nucleus of an atom and how the nucleus of atoms often behave. In order to talk about the nucleus of an atom, we need to understand three terms: isotopes, atomic number, and atomic mass. Isotopes are different versions of the same element. So down here are shown the three isotopes of hydrogen. What makes an atom, whatever element it is the number of protons it has. So each of these hydrogen isotopes would have one proton, because an atom with one proton is hydrogen. However, it can have different numbers of neutrons, and those are the isotopes. So each of these is a hydrogen isotope having one proton but a different number of neutrons. Next up, we need to understand the atomic number. The atomic number is listed here next to the symbol of an element. So the bottom number, whenever you're given a symbol of an element and then numbers next to it, the bottom number is the atomic number. And that means the number of protons, so the number of protons an atom has. And so that means hydrogen has one proton according to these symbols down here. Atomic mass is the number of protons plus the number of neutrons. Now, Mr. Shar, the chemistry teacher, would tell me that's actually not what atomic mass is. There is a better, clearer definition in chemistry, but for the purposes that we work with in physics, we can say that atomic mass is the number of protons plus the number of neutrons, and everything will be just fine. So over here on this iron atom, if we look at the symbol here for this one isotope of iron, we can conclude from this symbol and the information given by it that there are 26 protons and that there are 30 neutrons. Now you might ask, well, where did 30 come from? The atomic mass, the top number, is number of protons plus neutrons. So if I know there are 26 protons and the atomic mass is 56, I have to find the difference. 56 minus 26 gives me 30. So there are 30 neutrons in that isotope of iron. Now, you got to remember that the bottom number is the atomic number, or the number of protons, and the top number is the atomic mass, or the number of protons plus neutrons. There are three main types of radiation in physics. And as we talk about this, it may seem kind of intense, but actually dealing with radiation in physics is just adding and subtracting numbers. And so while the language could get confusing, just remember that down at its core, you're just going to need to add and subtract numbers to deal with radiation from the physics perspective. There are three main types of radiation: alpha, beta, and gamma. And these are the lowercase Greek letters, alpha, beta, and gamma. The fish is alpha, the B with a stick on the end is beta, and the overly curly Y is gamma. First off, alpha decay or radiation is not dangerous. The particles given off in alpha radiation can't even get through a piece of paper. The particles given off in beta decay can be dangerous, but can't get through things like aluminum, so even thin metals can block beta radiation. The final kind of radiation that we'll talk about is gamma radiation, which is quite dangerous. It can go through paper, it can go through aluminum, and it takes very thick lead to stop gamma radiation. So gamma radiation could get inside of a person easily and mess things up. Just to give you some context for like the bigger picture of what we're working on tonight. We differentiate the three types of radiation based on how they behave in a magnetic field. So we put a radium sample, and radium's a radioactive element, inside of a lead block, put a magnet over it, and then each of the different types of radiation went a different direction when they came out. The alpha particles went off this way, the gamma particles went straight, and the beta particles went off this way, which means that gamma has no charge, no electric charge. And I'll show you the actual magnetic field here in a second, but this experiment concluded that alpha particles have a positive charge, and it actually turns out they have a positive +2 charge, so the equivalent of 2 electron charges, but positive. Beta radiation is actually just an electron coming off, and it has -1 charge. So obviously the beta and the alpha particle should perform opposite. Also, what's neat is an alpha particle, whenever an element gives off an alpha particle, it's actually an atom of helium. And so alpha particles are just helium atoms. Gamma particles are really high energy, making them even more dangerous, and you can't see them. They're non-visible forms of light, non-visible electromagnetic radiation. Here's the diagrammed version. So this is the experiment conducted. Obviously, since the gamma particle went off undeflected, it has no charge, because a charge in a magnetic field would experience a force perpendicular. The alpha particle, if you do the right-hand rule here, its initial velocity was up. There's a magnetic field into the page. You get that a positive particle would experience a force to the right, meaning alpha is positive. The beta particle, a force to the left. By the right-hand rule, a force to the left. Alpha particle is positive because it followed the right-hand rule. The beta particle does the opposite of the right-hand rule, making it negative. And that's how we know the charge from each type of radiation. The first type of decay is alpha. It contains 2 protons and 2 neutrons, which is just a helium atom. And so basically, if you have this radioactive element, it will give out a helium atom, and it will change to a new element. So if an element loses protons, it's changing to a new element, because remember, the number of protons determines what something is. Alpha decay will decrease mass by 4 and atomic number by 2. So that means if we have element X, whenever it undergoes alpha decay, its atomic number will decrease by 2, and its atomic mass will decrease by 4, because remember, the top number is protons plus neutrons, so if it loses 2 protons and 2 neutrons, it loses 4 atomic mass. If it loses 2 protons, it loses 2 of its atomic number. Down here at the bottom is an example of what happens. Let's say we have radium that emits an alpha particle, meaning it loses 2 protons and 2 neutrons. So what you do is you basically just subtract what's lost from the original particle. So 226 minus 4 gives me 222. So I just took off 4 from the atomic mass, and minus 2 on the atomic number, giving me 86. Now, to figure out what element it is, you'd have to refer to a periodic table from chemistry. An atom with 86 protons is radon, and its atomic mass, we know by simple subtraction, is 222. And so, if you were asked a question of a particle undergoing alpha decay, that's literally all you do. You just subtract 4 from its atomic mass and 2 from its atomic number. It might be helpful in your notes because we're going to discuss 4 types of decay. Beta actually has a subgroup, to do a little chart that has the type of decay or radiation and the effect. So for my alpha, it's minus 4 mass, minus 2 protons. And that could just be a nice summary chart to have in your notes to easily look back at and to help in memorizing if you need to later. Try to get some of my slides with the atomic numbering over correctly. Anything that wasn't a picture got messed up, so I'll be correcting as we go. Here's our first example. A radon, which this should be written, Rn 22086. A radon 220 nucleus emits an alpha particle and becomes what? So if this thing emits an alpha particle, so we have radon, which is 22086 Rn. We know alpha decay means that it emits a helium isotope with 4 as its atomic mass, so 2 protons, 2 neutrons. 2 is its atomic number. And we will get out some element, so we don't know what it is yet, that has an atomic number 84 and an atomic mass 216. So let's see if from our answers we can just spot that. Wrong. You've kind of noticed what the computer did, it put them on the left and right. So wrong atomic mass on everything except choice A. Only one with the right atomic mass and has the correct number of protons. So even if you were confused by like, well, I don't have a periodic table, how can I look this up? You can pick it from the right answer from the numbers. Next is beta decay. The most typical kind is beta minus decay. And that happens when you have a neutron inside the nucleus that basically spits out an electron all of a sudden. So neutrons don't contain electrons, but all of a sudden a neutron in the nucleus creates an electron, spits it out, and then because the universe says you have to conserve charge, you can't just create charges out of nowhere, the neutron has to turn into a proton so that the total amount of charge in the universe is conserved. So in beta minus, what happens is one of the neutrons turns into a proton. So if you're imagining some element, and I'm just going to make something up, let's say its numbers were 3 and 2 for atomic mass and atomic number. Well, its atomic mass would stay the same because it's still going to have the same number of protons plus neutrons, but its number of protons has to go up by 1. So you think about it, its number of neutrons went down by 1, its number of protons goes up by 1. So we keep the atomic mass because it didn't change, but the number of protons goes up, so it changes to a new element. You can also have beta plus decay, which is where a neutron spits out a positron. Now you might not know what a positron is. A positron is an antimatter electron. We don't need to get into what that means, but a positron is an electron with a positive charge. You might be tempted to think, well, isn't that just a proton? Nope, because a proton has a different mass than an electron. So a positron is a thing that has the same mass as an electron, but has a positive charge. And so if that happens, a proton, I think I might have said neutron the first time, but a proton spits out a positron, and so that charge is conserved, this thing must now become neutral, because it gave up its positive charge, basically, and became a neutron. So if we had our atom from above, 3 and 3, if it decayed with beta plus, it would change to same atomic mass, because we've lost 1 proton, gained 1 neutron, but now it only has 2 protons because a proton had to turn into a neutron. You want to stop and add to that chart that I suggested earlier. Right, a potassium, correcting it, 40 nucleus emits a beta minus and becomes, so if we had potassium 40, notice I try to work these out and not go for the multiple choice, just a lot faster. So potassium 40, if it emits a beta minus, that means it gains a proton and loses a neutron. So now we have 20. So basically you can just think of, if you lose a minus, you must gain a plus. And if it was beta plus, if you lose a plus, you gain a minus. Either way it has to, or you gain a neutral. Either way it has to stay the same. So beta minus, we gain a proton. Beta plus, we lose a proton. So now I'm looking for something that has an atomic number of 20, and only one of our options has that. By the way, I want to pause here. Sometimes these numbers can be written with the atomic mass on the left and the atomic number on the right, but it always follows the convention of atomic mass is on top, so atomic mass is always on top, and atomic number always on bottom, even though they can change left and right sides. Okay, next example, the nuclide, which is just a fancy physicist way of saying a nucleus type thing of lead-214, pp E2-214, emits an electron and becomes nuclide X. Which of the following gives the mass and atomic number of nuclide X? So first I'm going to solve the problem. Looking at the multiple choice will confuse me. So I start out with lead-214. But if you notice the way I'm reading these, if I know the element name, I say it, and then you describe it by this number, the atomic mass, because the atomic number is implied by the element's name. Anything that has 82 protons is lead. Lead will always have 82 protons. And emits an electron. So if it emits an electron, stop and think about what kind of decay that is. That would be beta minus, because it lets out an electron, the negative indicating that. Remember that beta plus would be letting out a positron, not letting out a proton, although it does lose a proton and gain a neutron in beta plus. So if we lost a negative, we have to now gain a positive, so that means our new atomic number will be 83. And in beta decay, both types, the atomic mass stays the same because you lost one thing in a nucleus but gained a different one, so the overall number of things in the nucleus stays the same. So our atomic number is 83, so we can cross out everything that doesn't have that. And our atomic mass is 214. And there's our answer. And by the way, these are our AP release questions I'm giving you right here. We're jumping into the big stuff because this is as complicated as it really gets from the physics perspective. In chemistry, it would get more complicated than this, but this is all we need to know for the physics part of things. Now, gamma decay is a high-energy electromagnetic energy release. That is another way of saying it lets out a photon. So gamma decay lets out a photon, but it's not a typical everyday photon like the ones that let us see light. It is a high-energy photon that is looking for something at the atomic level to basically screw up. So gamma decay can knock electrons in other atoms out of place and really screw up stuff, especially in living organisms. Gamma decay, if it knocks a couple of electrons out of place in your DNA, can cause the development of cancer. So gamma decay is high energy and a really little vicious particle. But gamma decay is a pure energy release. It's not changing the mass of the element. So if we had, pretty sure this would be cobalt down here, CO. If we had cobalt undergo gamma decay, it would emit radiation, but nothing about the nucleus of the atom would change, except the amount of energy in it. So it releases energy, but the atomic mass and the atomic number stay the same. You just have to know that gamma decay is a release of energy in the form of a photon. So it just lets out energy all of a sudden. You might want to update your chart now. Here's a question that comes from a past AP exam. When a radioactive nucleus emits a gamma ray, and gamma is often expressed as a ray because it's not a particle that has mass, and so we talk about it as a ray like light. When a radioactive nucleus emits a gamma ray, the number of, stop for a second, let me pause the video, read the options, see what you think. Okay, let's go through these. And this also serves as a good review because the other answers are other types of decay. Option A. Protons increase by 1 while the number of neutrons decreases by 1. Well, what type of decay would that be? Stop and think about it. If you increase your protons, you had to lose a negative to gain a positive, so that would be beta minus decay. B. The protons decrease by 1 while the number of neutrons increase by 1. What would that be? Well, if you lose a positive, it's got to go somewhere, so the positron has to leave the atom. It's beta plus. You lose a proton and gain a neutron. And when I say gain and lose, it's really that a proton turns into a neutron, just in case you're picky about the language. C. Protons and neutrons each decrease by 2. What would that be? If your protons and neutrons each decrease by 2, that means you lost something that looks like this. You lost 2 protons and 2 neutrons. Remember, atomic mass is protons plus neutrons. And if you lose something with 2 protons and 2 neutrons, you've lost a helium atom. And if you've lost a helium atom, that is alpha decay. D. Protons and neutrons each increase by 2. Now this actually can happen, but it's not a type of decay. That would mean that the helium atom, something else left off, something else's alpha decay hit you, and you gained those things. It's called nuclear fusion, and something that we haven't been able to successfully create in a laboratory experiment, but we know it could happen. And finally, protons and neutrons remain unchanged. Gamma decay does not change the number of protons or neutrons, it simply releases energy. So that would be our correct answer. And that's 3 AP questions that are likely to show up because it's hard to ask these things other ways. So those questions that you've seen today might be asked with different elements, especially the ones for beta and alpha, but those are the exact type of questions you'll get on the AP exam.